Flutube. Get it straight.
Kinematics, and we're going to be looking at the conservation of momentum. This is a kind of a difficult derivation, but I hope it makes sense to you based on stuff that we've talked about before. And then later, next week, we'll get into plane potential flow, and we'll talk about the Navier-Stokes equations, which are very general flow equations when we start putting all this together, including viscosity. So for now, let's just look at the linear momentum. Remember when we looked at it in the Reynolds transport theorem in chapter 5, it looked like this, where we have the net change of momentum over time in the system is equal to the change within the control volume plus whatever is coming in over the control surface. If we give momentum the vector p, capital P, so this is not pressure, it's momentum, we like to remember equate this momentum in the system to the net forces acting on the system. And here we can define this momentum vector p as the integral of the velocity vector times dm, the differential mass. So let's look at these forces. So forces, differential forces have to equal the differential velocity, the total derivative of the momentum, and that's equal to differential mass times acceleration. So basically force equals mass times acceleration. So there's two types of forces acting on this small volume. Surface forces are forces that, as they sound like, they act on the forces of the differential volume. And then there's body forces that are forces distributed through the entire volume. So a body force is, for example, gravity, the derivative of the force in the g direction, or we could talk about it in three components of g. Surface forces are a little bit different and a little more interesting for us from a fluid perspective. There's one normal force and two tangential forces. So the normal forces are called normal stresses. They're related to the pressure. If you remember that relationship between pressure and stress, that negative inverse relationship. And then shear stresses are forces along the edges of the cube. So they're often offered by another cube on the other side. And you sort of get the feeling of these shears by the tau in here, these surface shear stresses. We're probably going to start talking about viscosity pretty soon. If you recall, that's what we used for shear. We use sigma for normal stress and tau for shear stress. So if we look at the sum of the forces in the x, y, z direction, and I know this gets pretty busy, but let's just focus on the x direction. We have the normal force, sigma xx, acting on the x face, and we have shear happening on two of the sides, and then we have the differential volume. So here's the total stresses acting times the volume. That would be the differential forces. And so we can do the same. I won't go through it in y and z, but it's basically just reorienting yourself. Right now it's written for the top one. But if you change those arrows around to the other faces, you'll get these two as well. So here's the differential force. It's a function of the forces in the x, y, and z. And these differential forces are sum to mass times acceleration, if we remember the body force too. So these up here, no, these ones up here do not show the gravity term that we talked about a moment ago. So that's the body force. So the mass is expressed here by rho times the differential volume size, dx, dy, dz. That's the volume times rho, gives you the differential mass. The acceleration is just as it was before, this term that has the local acceleration and the convective acceleration in it. Here shown for all three components. So we have that mass times acceleration that turns into this giant term, and that would, in the x direction, that would equal the sum of the body and surface forces in the x direction, and similarly in the y direction and in z direction. So if we put in the body forces, and this time you see the gravity here and the surface forces shown here. now have this large thing that basically says here's mass times acceleration, difficult to write, is equal to force. And there's several kinds of forces here and here. So that gives us our momentum equation, which is a very general equation, and it's so general that they call it the equations of motion. So here it is, where we've got the mass times acceleration is equal to body force, surface forces. So you can imagine back to the Reynolds transport theorem where we had the external forces summing to mass times acceleration. We had the external forces equated to the momentum. You can see the momentum and the forces in here. And so we've covered quite a bit in chapter 6 today, and got a little bit longer to go. Chapter 6 is a kind of a meaty chapter. Try to maybe watch these a couple times and get a feel for it and look at some example problems.